Hey AP Pre-Calc, it's Miss Adams from Flamingo Math. Let's finish up our lesson today on parametric functions. Our skills today are going to be a little more difficult than yesterday. We're going to start in example 6, finding a rectangular equation for our graph and curve defined by x equals 6 cosine t and y equals 4 sine t. Then we're going to sketch the curve over the set of real numbers. You can see here in the steps that they've given us some clues for what we ought to be thinking about. And first I'm going to think about taking this first equation, x equals 6 cosine t. I'm going to divide both sides by 6 so that I have x over 6 is equal to the cosine of t. And doing the same thing with the y equation, y divided by 4 is going to be equal to the sine of t. And our hint is that we should be able to use sine squared plus cosine squared equals 1. So the way that can happen would be if I squared the left side and squared the right side of each equation, and then thought of this as a system of equations where we could add the two equations together, we would end up with x squared divided by 36 and y squared divided by 16 is equal to cosine squared plus sine squared, which is 1. So we're using that identity here in our steps or our hint. So what does that give us? If you have seen conic sections before in earlier classes, you know this is an ellipse centered at the origin, and the ellipse goes out 6 units on the x-axis and 4 units on the y-axis, and it forms a nice smooth ellipse as we work our way around. Now, if you made a table where you were given t as pi and 3 pi over 2 and 2 pi, you could evaluate that your x and y coordinates would be -6, 0, 0, -4, and 6, 0. So if you started over here at 6, 0 when t was 0, you would work your way around to -6, 0 here at pi, and then 0, -4 at 3 pi over 2, and you would stop back at 2 pi. So that's a little bit trickier than what we saw on the first day. Example 7 wants us to find 3 different parametric equations for the function y equals x squared minus 5. Now get straight in your head what x squared minus 5 looks like. It's a parabola that's up on both left and right. It has a vertex at 0, -5. So the first thing we could do for x equals t up here, if x equals t, if x equals t, then y is going to be t squared minus 5. If x equals t squared, then y is going to be t to the 4th minus 5. And if x equals t cubed, then y is going to be t to the 6th minus 5. And we got those by substituting into our given y. We could use a graphing utility and set the parameter from -infinity to infinity. I'm not going to take video time to do that, but we could do that to compare. And then if we compared the 3 parametric curves for part C, are they all equivalent to x squared minus 5? Yeah, but when you look at the 3 curves, this second one, when x equals t squared and y is t to the 4th minus 5, it is not equivalent. And the reason it's not equivalent is because only the points from 0 to the right are obtained, while the domain for x squared minus 5 is all real numbers. So this one would not have the same graph. And like I said, it would be great if you took your calculator and looked at that on your own. So I said it something like this. When you graph x squared, x is t squared, and y is t to the fourth minus 5, this is the graph you get. It's not the same as our parent graph because we only got the points for x greater than or equal to 0 when the domain of our original function was all real numbers. So you could explore that on your own. For example 8, this will be our last example in this lesson. We want to find the parametric equation for the given conditions. We have a parabola. The vertex is at 2, -3. The parabola opens downward, and we know the parent function for the general form of a quadratic function. So if our parabola opens downward, then we know that the a value has to be -1 to get that to happen. And we know the h value is 2, and the k value is -3. So substituting into that general formula, we have -1 times x minus 2 quantity squared, and the k value is down 3. So if we add time as a third variable, then our equations could be x equals t and y equals -1 t minus 2 squared minus 3 for t greater than or equal to 0. So we can sketch that in the grid given to us at the right. Now here's our problem. We only have t greater than or equal to 0 for time, but if we had time less than 0, I'm going to do that in a different color. So if we allowed the case where time was negative, we could get the other half of that parabola, 1, 2, 3, going over here to get the full parabola of the given conditions. A was negative, the graph was concave down. We had a vertex at 2, -3, and the domain in our first case is all real numbers for the domain. Thank you for joining me in this first lesson in Unit 4.